sections of the beams. As with columns, the end conditions have a considerable influence on the stability of the member. This support is fully fixed and restrains all component distortions, whilst the one on the right is a simple support which permits rotations in both the vertical and the horizontal planes. This test shows two slender beams of identical cross-section. One is a cantilever. The second is twice as long and is tested as a simply supported beam. Load is applied to the cantilever and failure is due to instability. The simply supported beam is also loaded. Again, failure occurs due to instability. It can be seen that the distorted, buckled shape of the cantilever is approximately the same as either half length of the simply supported beam. Viewed from above, the out-of-plane deflections of the cantilever and either half length of the simply supported beam are obviously similar. This is analogous to the comparison between a pin-ended strut, corresponding to the simply supported beam, and a cantilever strut, corresponding to the cantilever. This correspondence is not exact, as the behavior of beams is more complex, as it also involves torsional effects. The end restraint provided to a beam has a major influence on the occurrence of instability, and can be utilized to enhance the load carrying capacity whenever instability is likely to occur. An alternative way of increasing load carrying capacity is via the provision of bracing. Consider again a slender, simply supported beam. If it were unbraced, it would fail by instability, with buckling occurring over the total length of the beam. Bracing is introduced at the third points and attached to stiff framing. This bracing is in the form of light, flexible wires. Load is applied and, relative to the unbraced beam, the carrying capacity is considerably enhanced, as buckling can now only occur between braced points. On plan, the elastic horizontal distortions show that the effective length of the beam is reduced to 1/3 of its overall length. For example, the shape of the middle third is the same as the buckled shape for an unbraced, simply supported beam. This results in a corresponding increase in the critical moment. In this example, although the bracing is very light, it has considerable axial stiffness. This stiffness is important. If the support for the bracing is less stiff, then, whilst the strength of the bracing remains the same, the effective restraint has been significantly reduced. Load is applied. And instability now occurs at an intermediate load, higher than that for the unbraced system, but well below that of the system with a very stiff bracing. Often in structural situations, continuous bracing is provided to the compression flange. For example, by a floor slab which is carried by the beam. In such cases, the beams are prevented from moving laterally, and lateral torsional instability cannot occur. Bracing is most effective when restraining the compression flange, as it is essentially the compressive action in this region which causes the instability. In this building, the floor slabs are supported on shelf angles, a form of construction which provides good restraint. Similar considerations apply to bridge construction. Here, the longitudinal beams may be restrained on their upper surfaces. It is important to remember that, with a continuous beam supporting a floor slab or bridge deck, the slab will provide restraint in that region of the beam which is subject to a sagging moment. But, adjacent to the reactions, there will be regions subjected to hogging moments, where the lower flange is in compression, and bracing of this flange too may be necessary.